Okay, so let's start. Welcome to week 11's problem solving session for computation complexity theory. What we'll do what we'll do today is we'll first solve last year's week 11 assignment. Then we'll solve this year's week 11 practice assignment. And then, depending on how much time we'll have, we'll solve this year's week 10 assignment, whose deadline is passed. Okay, so am I recording? Yes. Okay, so let's start. The first problem is that any cube be a function from 0, comma 1 to the n, cross 0, comma 1 to the n to 0, 1. Be the non-equality function, that is, neq x, comma y equals to 1, if and only if x and y are not equal. Which of the following sets, which of the following sets is or are a Fooling set for this function? And we are supposed to select all the correct options. The first option is uh, the set of all tuples x, comma y, such that x equals to y. The set of all tuples x, comma y of where x and y are both n-line strings, so that x not equals to y. Uh, the set x, comma y of all strings where x equals to 0 to the n and y can be any string of length n. And the set 0 of tuples 0 to the n, comma 1 to the n and 1 to the n, comma 0 to the n. So the correct answers to this problem are options A and D. So let's see why. So let's first recall what a Fooling set is. So is not equals to f of x prime comma y or f of x yeah, f of yeah. Okay, so now let's go over all the sets and see if they are Fooling set or not. So for A, Yeah, so for A, the, for all x comma y in S, so x and y are the same. So any q of, okay, let me write it like this. For all x comma y in S, x equals to y. So any q of x comma y equals to any q of, which is 0 because they are equal, right? So the first condition is satisfied. And what about the second condition? So for all x comma y and here I should mention that these are not equal. Yeah. So for all x comma y not equals to x prime comma y prime in S, y is equal to x and y prime equals to x prime. So any q of x comma y prime is equal to q of x comma x prime, which is 1 because x and x prime are not the same. Otherwise, these two would be exactly the same. Yeah, so the second condition says that uh, either any q of x comma y prime must be different from any q of x comma y, or any q of x prime y should be different from any q of x prime y prime. So one of these conditions, at least one of these conditions, in particular, this is satisfied. Actually, this would also be satisfied, but this is satisfied and there is an or over here. So we can conclude that the second condition is also satisfied. So A is a Boolean set. What about B? Yeah. So for B, for all x comma y in S, y is not equals to x. So 1 because they are different. So at least the first condition is satisfied. But what about the second condition? So uh, let me pick 0 to the n, 1 to the n, and 0, 1 to the n minus 1. Yeah, let me do it like this. 1 to the n, 0 to the n in S, and clearly these are different, right? So now f of, no, I want these to be not equal, right? So I should choose something like 0, 1 to the n minus 1, and 1, 0 to, this should work. So both of these are clearly in S because, yeah, the two strings are not equal in both of the tuples. So now any q of 0 to the n, 1 to the n minus 1, this is 1, and any q of 0, 1 to the n minus 1, and 1 to the n is also 1. And what, oh, I lost connection. Yeah, and what the condition tells us is that at least one of these should be equal to 0, but that is not satisfied. So B is not a full insert. Similarly for C, so what is it? It's 0 to the n and 0 comma 1 to the n. So for 0 to the n comma 0 to the n, which is in S, let me leave some space. S n e q into 0 because they are equal, but for 0 to the n comma 1 to the n, which is also in S, and eq is 1. And so these two are different. So the first condition itself is not satisfied, and this cannot be a Fooling set. So not a Fooling set. So, yeah, so C is also not a Fooling set. And now let's look at D. It's 0 to the n, 1 to the n, 1 to the n, 0 to the n. So both the strings are different. So this is 1. So the first condition is satisfied. And what about the second condition? So the second condition holds for all pairs. But over here, there's just two pairs. So we just need to check that 0 to the n, comma 0 to the n is equal to 0. And which is not equals to f of 0 to the n, comma 1 to the n. So second condition is satisfied. In fact, yeah, we can also write this. So the second condition is also satisfied. And so this is a Fooling set. So the answers are A and B. Okay, so now let's look at the next problem. So the next problem is consider the function f from 0, comma 1 to the n cross 0, comma 1 to the n to 0, comma 1. We can view the inputs as the binary representations of two integers x and y, and let z be the product of x and y. We define f of x comma y equals to 1 if and only if the product of z equals to 3 mod 5, right? What is df? The deterministic communication complexity of f. The options are order 1, order log n but not order 1, order log square n but not order log n, and order n but not order log square. So let's see. So okay, we know. Okay, so okay, so f of x comma y is to 1 if and only if z equals to 3 mod 5. But z equals to xy, so this is just now xy mod 5. Rather, let me write it. So xy is congruent to x mod 5, y mod 5, whole mod 5. So if I replace this in the above equation, I get okay. So f of x comma y is 1 if and only if x modified times y modified. Oh, sorry, I should write equals 3 mod 5. is congruent to 3 mod 5. Yeah. So if we can, so if Alice sends X mod, Alice sends X, Bob is Y. So if Alice sends X mod 5 to Bob, then Bob can compute Y mod 5, multiply it to X mod 5, and then check if it's 3 mod 5, right? So the protocol is, okay, so in communication complexity, you can do two things. So either like at the end of the protocol, you can either require that one of the parties transmit the value of the function, or you require that they do not do it. But throughout this session, I'm going to follow the convention that at the last message of the protocol one has to be the value of the function sent by one of the parties. Okay, and so now Bob is going to send the value of f of x comma y to Alice. Now notice that in this protocol, this is required because otherwise Alice won't know what f of x comma y is. However, in some protocols, this might not be required. Alice and Bob can both dependently figure out what f of x comma y is, but will still require that one of the parties send the last message of the protocol is the value of the function itself sent by any of the parties. Okay, let me connect my charge here. Yeah, Bob sends one. Yeah, so now like this protocol clearly computes the function f of x comma y correctly because of these chain of implications over here. So all we need to do is like compute how many bits, the number of bits that are communicated between Alice and Bob in the protocol. So Alice sends x mod 5, and so x mod 5 is going to be less than 5, and any number less than 7, less than or equals to 7, can be expressed using just 3 bits, right? So this requires 3 bits, and Bob sends this requires so commit complex. Yeah, and 4 is order 1, so the answer is order 1. Okay, so let's look at the next problem. So the next problem is consider two functions f and f prime, uh, which are both from 0, comma 1 to the n, cross 0, comma 1 to the n to 0, comma 1. And what we have is that f prime x, comma y equals to f of x, comma y, then either x1 is 0 or y1 is 0, and f prime x, comma y equals to 1 minus f of x, comma y, when both x1 and y1 are 1. So we here x1 and y1 are the first bits of the strings x and y respectively. And which of the following statements is or are true? Select all that apply. The first is df equals to d prime, df prime. The second is df is less than or equals to df prime plus 1. The third is df prime is less than or equals to df plus 1. The fourth is df is less than or equals to df prime plus 2. Fifth option is df prime is less than or equals to df plus 2. And the last option is none of the above can be inferred from the information provided. Have like this needs to be worked out, so I won't ask you what the answer is, but yes, let's work this out. So first, notice that the roles of f and f prime can be flipped in the question. Without affecting the situation. Yeah, so okay, so over here I could easily have flipped the places of f and f prime, and you would still be in the same situation, right? So what this tells us is that the situation is symmetric. So if df prime is less than equals to df plus a, and df is also less than equals to df prime plus a. Why? Because let's say the current question gives us this, but even if I were to change the places of f, f and f prime, I still get land up in the same situation. Then by flipping, I can get this. So is this clear? Because then we only need to prove that either one of this is true, or this is true, or this is true. Is this fine?
Yes.
Yeah,
Yep.
yeah. Okay, so now basically either this is true, or both of these are true, or both of these are true. Yeah, I'll say that this is not true right from the very beginning. Okay. So now let's see what is true. So consider the following protocol. So, okay, so if you want to relate the communication complexities of F and F prime, one way to go about doing this is to construct a protocol from for F prime using the protocol for F, right? So that is exactly what we'll do. And here's how we are going to do. So, okay, so what is the difference between F and F prime? So the value of F prime, the relation between F and F prime depends on the first two bits of first two bits of X and Y, right? So what Alice can do is send X1 to Bob, and then Bob knows whether they should compute fx comma y or 1 minus x comma y, right? So then Bob can immediately start executing the protocol for that function for f, right? And at the end, what Bob can do is if x1 was 0 and y1 is also 0, then sorry, if x1 were 0 or y1 were 0, then Bob has at the very end of the protocol has to send f of x comma y. And if both were 1, then it has to send 1 minus f of x comma y. So one way of doing it, this would be like for Alice to send x1 and Bob to send y1, and then they start a protocol for f. But that would immediately say that d of f, that would immediately say that at least 2 bits of extra communication is required. But since we want to minimize the number of bits communicated, let's start with just sending x1 and see if we can get this. Okay, so if we still can't get this, then we would end up in this. So, but since we want to minimize the number of bits sent, let's just try to construct a protocol where only Alice sends x1 and Bob does not send y1. Okay, so the protocol is this: Alice sends x1 to Bob, then they execute for f to compute f of x comma y. Once Bob gets f of x comma y at the end of the protocol, he sends f prime. Okay, he computes uh, f prime x comma y from f of x comma y as follows. If x1 equals to 0 or y1 equals to 0, f of mhm, and he then sends. Yeah. So, so this is the protocol for f prime x. Now, first of all, let's convince ourselves that this will work. So Alice has sent x1 to Bob, and Bob already has y1. So now Bob knows whether he should, at the end, compute this or this, right? So they execute the protocol, compute f correctly, and then since Bob knows about x1 and y1, he can compute f of x, f prime x comma y from f of x comma y properly, right? So at least this protocol correctly. Okay, so up till this point, this like at this point, now Bob knows the correct value of f prime x comma y. However, since Alice did not have y1, there is no way for Alice to know what the value of the function is, right? So Bob would have to send this to Alice. So yeah, there is no way for us to get away with just sending one extra bit of information. We tried that over here, but at the end we still had to force Bob to send f of f prime x comma y to Alice. So we need at least 2 extra bits of communication. So d prime t of f prime is less than equals to tf plus 2. Less than or equals to because we just demonstrated one protocol for f prime, right? There can be some another protocol for f prime which is much more efficient, and d is supposed to be the minimum communication complexity. So we have shown a protocol with this much communication complexity. So df prime is definitely upper bounded by this, but it can be less than this. So we need to include a less than equals to. Okay. So this option is correct. But yeah, from what we argued over here, it means this is also correct. Yeah. So is this fine?
Yes.
Yeah. So let's the next problem then. So the next problem is given a function f of x comma y from 0 comma 1 to the n cross 0 comma 1 to the n to 0 comma 1, let mf be the communication matrix of f. Suppose that the determinant of mf is 32. Then the deterministic communication complexity of f is at least what? 5, 32, n over 32, or n? So which of these is the correct answer? Okay, so yeah, the correct answer is n, and let's see why. So we know that the deterministic communication complexity of any function is at least log base 2 of the rank of the communication matrix. Okay, and now what information do we have over here? Here, determinant of MF equals to 32. So the determinant is non-zero, right? Now, when can the determinant of a matrix be non-zero? Uh, this is possible. Okay, determinant is non-zero. The determinant of MF is non-zero if and only if uh, MF is invertible, and MF is invertible if and only if all of its rows are linearly independent and all of its columns are linearly independent, which means that MF is invertible if and only if uh, MF is a full rank matrix. That is, the rank of MF is equal to the number of its rows or the number of its columns. Now, MF is an 2n cross 2, to the n cross 2 to the n matrix. So, rank of MF is 2 to the n. And DF is at least, which is n. Yeah, so M, the deterministic communication complexity is at least n. So over here, determinant being 32 is not important. What is important is that the determinant is non-zero. So instead of 32, even if we had some other non-zero number, this would still work. Yeah, I hope this is fine. So so now let's look at this year's week 11 practice assignment. So the first problem from the practice assignment is that in the two-party communication, sorry, in the two-party communication complexity model, what is the computational power of the individual parties Alice and Bob? The options are log space, T, T space, X prime, and unlimited computational power. So which of these is correct? Is correct answer is option E. So in the communication complexity model, E, yeah, the correct answer is E, yes. Yeah, so in the communication complexity model, we don't, what we are interested in is the number of bits that they need to communicate with each other to compute the function. We don't care about how much computational resources each individual party has to utilize to compute the function. And so we let both the parties be unbounded. We let both of them have unlimited computational power. Yeah, so the answer is option E. So let's look at the next problem. The next problem is, suppose Alice and Bob need to compute a function f from 0, comma 1 to the n cross 0, comma 1 to the n to 0, comma 1, and they use a protocol pi to compute f. So which of the following choices indicate the worst case number of bits communicated by pi? The options are the number of ones in the matrix MF, the number of nodes in the protocol tree, the height of the protocol tree, and the last option is the number of leaves in the protocol tree. So which of these is correct? Yeah, it's the height of the protocol tree. Yeah, so and the reason is that okay, so the height of a tree is equal to the length of the longest path. The longest root to leaf path, the protocol tree. Each path corresponds to the execution of the protocol on some inputs. So, okay, also uh, the number of bits communicated in this execution is equal to the length of that path. Uh, yeah, and so the worst case complexity, number of bits that need to be communicated in the worst case, is equal to length of the longest path. And this is equal to the height. Yeah, so this is why the number of bits that you need to communicate in the worst case is equal to the height of the tree. Now let's look at the next problem. Yeah, so the next problem is, it's similar to one of the problems that we solved before. Consider functions f and f prime from 0, comma 1 to the n cross 0, comma 1 to the n to 0, comma 1. Suppose f prime and x, f prime x, comma y and f x, comma y are the same for all values of x comma y equals to 0 comma 1 to x comma y 0 to comma 1 to the n, except when x and y are both 0 to the n, right? The all zero input. Then which of the following statements is or are true, and select all that apply. The options are also the same. df equals to df prime. Df is less than equals to df prime plus 1. Df prime is less than equals to df plus 1. Df is less than equals to df prime plus 2. Df prime is less than equals to df plus 2, and none of the above can be inferred from the information provided. So again, this needs to be worked out. So I won't ask you what the correct answer is, but just as in that case, over here as well, if you were to switch the places of f and f prime, the situation won't change at all, right? So either this is true. Okay, first of all, this won't be true. Let me tell you that. So either this is true, or both of these are true, or both of these are true together, right? So we only need to decide whether this is true, or this is true, or this is true, right? So now let's do that. So as before, we'll just construct a protocol for f prime using a protocol for f. So okay, so over here, so even though like the answer is different when x and y are both 0 to the n, we don't need to send the entire 0 to the n. Alice can just signal Bob by saying that Alice can just send one bit to Bob to say that, okay, yes, my input is 0 to the n, right? And send another bit to Bob when the input is not 0 to the n. So it's completely possible for Alice to just send one bit 0 to Bob to tell Bob that its input is 0 to the n, and send 1 to Bob to indicate that her input is not 0 to the n, right? Now, in the previous case, we tried to just get away with having Alice send something to Bob, but Bob not send something to Alice because we wanted to minimize the number of bits communicated. But over here, both Alice and at the very beginning of the protocol, Alice and Bob must tell each other if their input is 0 to the n or not, because if both the inputs are 0 to the n, then they have to stop at that very point, right? So if x is 0 to the n, Alice sends 0 to Bob. If x is not equals to 0 to the n, Alice sends. Now, as I said, Bob also has to send something to Alice because otherwise they won't know whether they should stop or not. So, okay, rather let me do it like this. So, yeah. So, if x equals 0 to the n, Alice sends 0 to Bob, and if y equals to 0 to the n, Bob sends 0 to Alice. So, if y is also 0 to the n, then Bob knows that we have to stop the protocol now. So, Bob sends 0 to Alice, which is f of x comma y in this case, and they hold. Yeah, so if both x and y are 0 to the n, you just need 2 bits of communication. However, if this is not the case, then okay, so else, if x is not equals to 0 to the n. Okay, I still need to, okay, let me rearrange the statements. Yeah, so if both are 0 to the n, let me make that the first case. The second case is if x is 0 to the n, Alice else. But now 1 to Alice to tell Alice that they have to continue the protocol and they execute the protocol for. And what's the third case? The third case is, and in this case, Bob does not need to send anything to Alice because x x is not equal to 0 to the n, so they can directly start executing the protocol. So yeah, so in this case you need 2 bits. In this case you need 2 bits plus whatever you require for f, and here you just 1 bit plus whatever you require for f, right? And so yeah, this protocol is correct because when x and y are both 0 to the n, uh, the function they compute is the value they compute is 0, which is exactly the value of yeah the value of f prime when both are 0 and 0 to the n. And when at least one of them is not equal to 0 to the n, they execute the protocol for f, right? So they again compute f prime correctly because in this case f and f prime are the same. So the protocol uh, computes f prime correctly, and the number of bits required is so case one you just need 2 bits. Case two you need 2 plus df bits, and case three you need 1 plus df bits. Yeah, so the maximum of these is 2 plus df. So in the worst case, you need 2 extra bits. Yeah, so since this is true, d would also be true. And again, there's a lesser or equals to because there can be some protocol for f prime which is much more efficient than the protocol for f that we are given over here. Right. So is this fine? Yeah. So let's look at the next problem then. So the next problem is consider a function f from 0, comma 1 to the n cross 0, comma 1 to the n to 0, comma 1 that has the following property. For any x, comma y in 0, comma 1 to the n, we have f of x, comma y equals to g of x, where g is a function on a single input. So g is from 0, comma 1 to the n to 0, comma 1. In other words, the value of f is independent of the value of y. It just depends on the value of x. Further, suppose that there exists x prime and x double prime in 0, comma 1 to the n such that gx prime equals to 0 and gx double prime equals to 1, then what is the communication complexity df of f? 0, 1, 2, 4, n over 2, and n plus 1. So which of these is correct? Okay, so the correct answer is 1. So, okay. The value of function f only depends on the input x, which Alice has, right? So all Alice has to do is compute g of x and send its value to Bob, right? And the reason Alice needs to do this is there are there are x and x prime so that g of x prime is 0 and g of x double prime is 1, right? So if Alice did not send anything to Bob, then there is no way for Bob to figure out what the value of the function is. So Alice has to send at least one bit, the value of the function, to Bob, right? So the number of bits required is 1 and not 0. But let me just write down what I said. Yeah, so you need to send at least one bit. Is this fine? Yes. Then let's look at the next problem. So the next problem is consider a function f from 0, comma 1 to the n cross 0, comma 1 to the n to 0, comma 1 defined as follows. The function is equal to 1 if and only if x plus y, that is n bit binary numbers, is a multiple of 8. So what is d of f? 1, 2, 3, 4, 8, n over 8, and n plus 1. So like which of these is correct? Okay, so let's work this out. So f of is equal to 1 if and only if. Okay, but so we know this that x plus y is equal to 0 mod a is equivalent to, yeah, so here we can just place this. Yeah, so now Alice knows x, so she can compute x mod a 8 and send it to Bob, right? And Bob knows y, so he can then compute y mod 8. It has now x mod 8, so it can add these two up and check if that's 0 mod 8 or not, right? So uh, to compute f, all that needs to be done is Yeah. If yes, he sends 1. If no, he sends 0. Yeah, and so if at 0 mod 8, the value of the function is supposed to be 1. So now both Alice and Bob know it. Similarly, otherwise, the value of the function is supposed to be 0. So again, both Alice and Bob know it. So this protocol clearly correctly like computes f. Now we need to figure out the communication complexity. So x mod 8 is going to be less than or equals to 8, right? So it's going to be a number between 0 to 7, both included, and any number between 0 to 7, both included, can be written using at most 3 bits, right? So x mod 8 can be requires only 3 bits. So the communication complexity is 4 because Bob also sent this one answer to Alice. Yeah, first the answer is P4. Uh, I hope this is fine. Yeah, so this is fine. Then let's look at this year's week 10 assignment. I think, yeah, how many questions have we? Yes, I think today we have enough time to finish the questions. Yeah. So the first problem is, which of the following statements are most accurately describes the Tuda's theorem? Any language in PH can be decided by a deterministic polytime Turing machine with Oracle access with access to Sharpie Oracle. Any language in PH can be decided by a randomized polynomial time Turing machine with Oracle access to Sharpie. Any language in Sharpie can be decided by a deterministic polynomial time Turing machine with Oracle access to Sharpie. So which of these is correct? Yeah, A is correct. Yes. So Tuda's theorem says this, right? Yeah. So any language in PH can be decided by a polytime Turing machine with Oracle access to Sharpie, which is exactly the option, right? Yeah. So the answer is A. So now let's look at the next problem. So the next problem is, consider the Boolean formula phi equals to x1 or x2 or x3 and x3 or x4 or x5. The number of satisfying assignments of phi is what? So I won't ask you what the question is because here we need to work it out. So let's work it out. Okay, so yeah, one way to figure this out is the following. So x3 is common in both, right? So let's first fix the value of x3 and see what happens. So there are two cases. X3 is 1, right? Then x1, x2, x4, and x5 can each be either 0 or 1, right? So the number of possible assignments is so 2 times 2 times 2 times 2, 2 for each of x1, x2, x4, x5, which is 16. The other case is uh, x3 is equal to 0, then at least one of p1, and similarly at least one of x3 and x4 should be, yeah. So x1 comma x2 can be 0 comma 1, 1 comma 0, or 1 comma 1. And similarly, can also be, yeah, so for, we can pick any one of these three for x1 and x2, or and any one of these for x3 and x5. So the number of assignments is 3 times 3 is equal to 9. So the total number is 16 plus 9, 16. Yes, the answer is 25. Is this fine? Yeah. So then let's look at the next problem. So next problem is we are given this matrix and we are supposed to find the permanent of the matrix. So let's work this out. So now, if you recall, the difference between the determinant and the permanent was just a sign, right? So it turns out that just like you can compute the determinant by hiding the first row and the first column, computing the determinant of this matrix, then multiplying this with it, minus like hiding this, doing the same, and plus hiding this, doing the same. Similarly, you can compute the permanent by hiding this matrix, computing the permanent of this matrix, multiplying 2 with it, plus, so instead of minus, now we have to add, remove these, compute the permanent of this, multiply this with it, and same for here. So basically, you do exactly what you were doing in the case of the determinant, but now whenever you place a minus in the determinant, you don't do that. You just put a plus over here. So in the determinant, there are plus or minus depending on which determinant you were evaluating. Over here, there are no minuses. There are only pluses. Okay. So the permanent is 2 times the permanent of 2, 3, 5, 1 plus 1 times the permanent of 2, 3, 1, 1 plus 1 times the permanent of 2, 2, and 5. Yeah. And yeah, just now to compute the determinant, you would multiply these two and then subtract this product from them. But now again, there are no minuses in the determinant, so you have to multiply these two and then add this product to. So this is 2 times 2 plus 10 or 15 plus 1 times 2 plus 3 plus 10 plus 2. This is 17, 34, 5, 12. So it's 5 and 1 is 17. That's 17 times 3, which is 51. Yeah, so the permanent is 50. Is this fine? Yeah, so then let's look at the next problem. So the next problem is in the lecture videos we have seen the reduction from sharp 3 sat to 0, 1 permanent. Which of the following intermediate problems were part of reduction? Sharp 3 sat balanced, computing the permanent of matrix with minus 1, 0, 1 entries, computing the permanent of a matrix with 1 to m entries, and deciding if G has a perfect match. So which of these are correct? Yes, so yeah, A and B are correct, yeah. But I think C is also correct, right? Yeah, so all three are correct. And D cannot be correct because so the problem of finding a perfect matching is in P. So if that were part of the reduction, then what you would actually end up getting is that sharp sharp tree set reduces to some language in P. So sharp tree set is can be solved in a polynomial time, which would mean Ft equals to sharp P, and which would mean P equals NP, right? So D can't be correct. So is this fine? So let's look at the next problem. So next problem is suppose phi and psi are Boolean formulas on n variables x1 to xn, and suppose phi has k1 satisfying assignments and psi has k2 satisfying assignments. Then what is the number of satisfying assignments of phi or psi? The sum of k1 and k2, the product of k1 and k2, k1 plus k2 times k1 k2, the difference of k1 and k2, and cannot be determined from the given information. So which of these is correct? Yeah, so the correct answer is E, and let's see why. So one way to show that E is correct. So okay, first of all, I think we saw something like this last time, right? That to compute, so this would be K1 plus K2 minus K1 K, sorry, K1 plus K2 minus K3, where K3 is the number of satisfying assignments of phi and psi. So last time we saw that if we were given these three information, then we could have found out the number of satisfying assignments of phi or psi. So to show that none of A or okay, so to show that none of A or D are correct, like one way to argue is that given just K1 and K2, you can't find out K3, which might become complicated. Another way to do this is to show that is to come up with formulas such that need for is to come up with formulas phi and psi so that the number of satisfying assignments of phi or psi is neither A nor B nor C nor D. So let's do the second. So A is false. So let phi be okay. So let phi be any formula that depends only on variables x1 to xn. Rather, let me say x1 to xn over 2 and psi. Yeah, so we are assuming that phi and psi both depend on like disjoint sets of variables. So the number of satisfying assignments. Rather, yeah, I don't need to write this. I can just write sharp phi or psi. So since both phi and psi depend on disjoint sets of assignments, sorry, disjoint sets of variables, you can pick any assignment. You can pick, okay, so you can pick any assignment, satisfying assignment of phi, and that would give you the, and okay, so you can pick any satisfying assignment of phi. So you can pick any particular value of x1 to xn and let psi be anything. So let xn plus 2 n over 2 plus 1 to xn be anything. Or you can pick these to be any satisfying assignment of psi and let these to be anything. So this is okay. Let me just do it like this. This is equals to sharp pi times 2 to the n over 2 because there are n over 2 variables plus sharp psi times 2 to the n over 2 minus sharp phi times sharp psi because this because okay, what is it over here? Over here it's satisfying assignment of phi as well as psi, but I would have counted it once over here and once over here, so I need to subtract it, right? So this is 2 to the n over 2 k1 plus k2 minus k1 k2 and okay, so it's so all we now need to do is to come up with real values of k1 and k2 such that this number is not equal to k1 plus k2, right? So if k1 equals to k2 equals to 1, then this is 2 to the n over 2 times 2 minus 1 is which is not equals to 2, which is equals to k1 plus k2, assuming yeah, n is greater than equals to like put 1, yeah, let's just say n is greater than equals to 2. So this is, yeah, it's at least 3, yeah. Yeah, and it's easy to come up with formulas where k1 and k2 are 1, right? Something like x1 and x2 and x3 up to xn over 2 and xn plus xn over 2 plus 1 and xn over 2 plus 2 and so on up to xn would work, right? So A is not true. What about B? So use the same, okay, would that be difficult? Yeah, no, it is easy, yeah. So use the same example as in A. So yeah. Uh, yes, okay, I won't write it, but yeah, sharp phi or phi is still this. Now let K1 equals to K2 equals to 1 again. Then 2 to the n over 2, K1 plus K. Okay, then I think n should be equals to 2 maybe. Yeah. So B is also false. What is C? It's K1 plus K2 times K1 2. I think we can again use the same example. Yeah, I could have just copied this and rewritten this. And again, let K1 equals to 1. Then K1 plus K2 times K1, K2. This is 2, and this is not equals to 2 to the n of 2. Okay, I might. I can just yeah, copy the value of this. It is just this. And yeah, again, let me just say, yeah, because this is going to be at least 3. Yeah. So this is also false. What about T, K1 minus K2? I think it will be the same again. Okay. Let me just copy the entire. Yeah, then yeah, so D is also false. Yeah, so all four are false, only E is correct. So now let's get the next problem. So this was a part of the subjective assignment. Uh, the problem is so three set balanced is a decision version of the counting problem sharp three set balanced. That is, you are given a three set formula phi where every variable appears in the positive and negative form with the same number of times, and you need to check if phi is satisfiable or not. And we are supposed to show that three set balance is NP complete. So to show that three set balance is NP complete, we need to show two things. Number one, it is in NP, and number two, it's NP hard, right? So first, let's show that it's in NP. Okay, so all we have to do is give us find our certificate and a a poly-size certificate and a polytime verifier, right? So given phi, okay, for DTMM, and ATM formula phi and say x1 to xn, and yeah, so it first checks if each variable appears in the positive and negative form exactly the same number of times, and if it does, then it checks that. Yeah, so now this verifier correctly decides whether or correctly verifies whether phi is in x1 to x is in three-set balance or not, right? Because for it, it is in three-set balance if and only if every variable appears the same number of times both in both positive and negative forms, and it is satisfiable, right? So, hmm, okay, and now okay, so the certificate over here is W, and size of W is less than or is like exactly N, which is Pauli in the size of the int. Yeah, and the running time of M is okay. So for the first step, all it needs to do is like go over the formula n times, one for each of the x i's, and every time it encounters x, count. Okay, so every time it goes over the formula, it keeps two counters, one for xi, one for xi complement. Every time it sees xi, it adds one to the counter for xi. Every time it sees xi prime, it adds one to the counter of xi complement, and so on, right? So the first step can be carried out in poly n time, sorry, poly size of pi time. And the second step, it just has to put the values of W1 to W and in case of X1 to Xn and check if evaluate the formula. So this can also be done in poly time, right? So the running time is, and so, yeah, also, yeah, so we have a polytime certificate, polysize certificate, a polytime verifier that verifies the correctness. And this certificate will only exist if the line, if uh, phi is in three-set balance, right? So this means that three-set balance is in NP. So is this fine? Then we can move on to NP hardness. Okay, I hope it's fine. So now let's look at why this is NP hard. Yeah, so to show that three-set balance is NP hard, we can reduce from any NP commit problem. So since three-set balance is very much related to three-set, we'll just use three-set, right? So we'll reduce from three-set. The reduction is as follows. So let phi be a three-set instance. Let me call it shell. Uh, so if okay, okay, let's let zero do nothing because both xi and xi coordinate appear the same number of times. Then if so if bi is greater than zero, then xi appears bi many times more than xi complement. So we should add xi complement bi at least be exactly bi many times, right? So we are going to add these clauses. Right? Yeah. This will only work if the difference is even. And what if the difference is odd? Okay, yeah. Oh no, I need a chair as well because I need distinct variable. Wait, too shy for chain P two. Here Zi comma j comma 1 Zi comma are distinct variables. Distinct and new variables. So I think we can simplify this instead of doing it in two cases when bi is not even and odd. So if I were to just keep this would work. Yeah, okay, I don't think I need this. I don't think I need this. Yeah, I think this would work. And if pi is strictly less than 0, and again, yeah, this is the same here. Zi comma j comma 1, Zi comma j comma 2 are distinct and new variables. Yeah. So what we have done is just this. So if the number of times that xi and xi complement appear the same is the same, we don't need to do anything. That's this. If xi appears more times, then we need to add xi complement a few more times. So that's here. And if xi complement appears more times, then need to add xi a few more times. That's what we've done here. And finally, after this is done, we also add of phi to psi. So now psi looks like phi along with an end of few clauses that look like this, right? So for all I in psi. So at least psi is a balanced formula, right? And this is true because, like, let's say xi appeared more times, bi many more times, and we have added xi complement bi many more times, right? And similarly in the other case. So now at least psi is a balanced formula, right? Also, psi can be computed in polynomial time. Well, because uh, okay, so if phi had m clauses, then it can have then okay, bi can be at most 3m, right? So we all you have to do is for every I add at most 3m clauses of this type or 3m clauses of this type. And so all you need to do is, in the worst case, add 3m and more clauses, where n is the number of variables. But this is still poly in n and m, right? So you can compute psi from phi in polynomial time. Okay. So now, this means that at least this function of that reduces this function to reduce phi to phi to psi is a polytime commutable function. Now we need to show that this is a valid reduction, right? And for that, what we need to do is we need to show two. So we have already observed that psi is balanced. So we only need to show it's satisfiable. Oh, I lost the connection again. Yes, I lost network connection for a while. Can you hear me?
Yes.
Okay, yeah. Psi is satisfiable. So phi is satisfiable. So let then a1 to an along with okay for all I for all. Why? Because psi is just phi and, and these extra clauses. And since I've made these two one, the extra clauses are always true. So as long as phi is satisfied, psi would also be satisfied. And now we need to prove the converse. Is equal to phi and some clauses. So if phi were not satisfiable, uh, psi would also not be satisfiable. Yeah, because for uh, and to be and to be true, both have to be true, right? But if phi can never be true, then neither can psi, right? So if psi is in three-set balance, that means satisfiable, right? So this proves both the directions, and so this proves that what we have done what we have constructed over here is a validated action. Yeah, so and it's polynomial. So three-set balance is NP hard. So is this fine? Yeah, so I think this is all I have for this week. Yeah, so if we have no other questions, we can end early today.
Yeah, it's okay for today.
Okay, yeah. Okay, bye.